Okay, good morning, everyone. So we're going to start today's class. All right, the first thing is I want to make an announcement, which is that the midterm exam is canceled. Okay, so we're not having a midterm exam this week, and we're not having any midterm exam at all. Okay, and the reason is because because we can't really meet in person for this class. If we have an exam, we would have to do it online, which is very hard to do because we have a very large class, so it's hard to do an online exam for so many people. Okay, so we're going to cancel the exam, and I sent a announcement about this. So we're going to redistribute the points for the exam to the project and the final exam. Okay, so I think both the project and the final exam will now be worth 10% more of your final grade. Okay, so hopefully, by the time of the final exam, so we're going to do the final exam after week 16. Okay, so hopefully by that time, things are back to normal, and so then we can do a in-class exam. All right, so that's the announcement. And so then next, let's get to our class, which is that we're going to keep talking about NP completeness today. Okay, and so we talked about we defined NP completeness previously, and we showed one example where you could show the clique problem was NP complete, right? And the way that you do that is that you take an existing NP complete problem and you reduce it to clique. Okay. And so because so we took 3-SAT and reduced it to clique, right? And so because all other NP problems reduce to 3-SAT, because 3-SAT is NP complete, right? And then 3-SAT also reduces to clique, then that means that all NP problems reduce to clique, right? And also clique is an NP problem, and so therefore clique is an NP complete problem. Right. So the hard part is to show this reduction. Right, because what you need to do is, in order to reduce 3-SAT to clique, you need to take an instance of 3-SAT, which is like some sort of Boolean expression, right? And then you need to convert that into a graph, which is an instance of the clique problem. And this conversion this reduction process, well, first of all, it needs to be efficient, right? It needs to run in polynomial time. And second, it has to have the property that if you have a satisfiable 3-SAT instance, then you have a graph which does have a n/3 clique. And if your graph has an n/3 clique, then also the Boolean expression is satisfiable, right? So basically, the Boolean expression and the graph that you transform it to are equivalent, right? They're either both solvable or both not solvable. Okay, so that's the general approach to proving that problems are NP complete. And so now I want to do some more examples of these reductions, okay, because it helps to see lots of these examples if you want to know how to do them yourself. Okay, so the next problem that we're going to show is NP complete is a subset sum. Okay, so we talked about this problem previously, and remember that the way it works is you have a set of numbers. Okay, S is a set of numbers, and then you have a target value T. And now the question is, can you find a subset of these numbers such that they add up to T? Okay. Right. So we, Now, first of all, so we're going to show that this problem is NP complete. So first of all, we need to show that it's in NP. Okay. And so this is pretty easy because remember, for the NP, you need to give a certificate or witness. Okay, so our witness in this case is that we're going to give a specific subset S prime of S. Okay, so now if you have a yes instance of subset sum, then this means that there is some sort of S prime which adds up to T. Okay, so then if you just provide that subset S prime, right, then the verifier is just going to add up all the numbers in S prime, and if it's equal to T, it's going to accept. So when it is a satisfiable instance, we can just provide the verifier the subset, and then the verifier will add it up, and it equals T, and it accepts. And otherwise, if it's a no instance of subset sum, then any subset S prime you give to the verifier will not add up to T, right? And then the verifier is going to see that it doesn't add up to T, and so it will reject. Okay, so this shows that subset sum is in NP. So next, we need to, so in order to show that it's NP complete, we need to take some sort of NP complete problem and reduce it to subset sum. And again, you can choose any NP complete problem you want to reduce to subset sum. Okay, but sometimes, if you choose the right problem, then it makes your reduction process easier. Okay, so the problem we're going to choose is again going to be 3-SAT. Okay, so remember that we used 3-SAT to show that clique was NP complete, and again we're going to use 3-SAT to show that subset sum is NP complete. Okay, and actually 3-SAT shows up in many of these reductions. Okay, it's often the problem that you use to prove another problem is NP complete, and it's just 3-SAT is a very flexible problem, and it's also very structured. Okay, because you have these clauses, right? The clauses only have like 3 literals in them, and so it's kind of a very fixed format what the 3-SAT instance looks like, right? Whereas if you try to do reductions from some other problem, let's say a graph, right? Then the graphs are kind of like graphs don't really have much structure to them, so it's kind of harder to do these reductions starting from a graph problem. Of course, in some cases, it is possible to do these reductions starting from graph problems. Okay, so later we're going to see another reduction where we actually start from a graph problem and then reduce it to another graph problem. Okay. But still, for many of these reductions, we start from 3-SAT. Okay, so then what we need to do is that we're given a 3-SAT formula phi, right? And then you need to do a reduction, meaning that in polynomial time, we need to construct an instance of subset sum. So we need to construct a set S and a target value T, okay, such that if this formula phi is satisfiable, then there is a subset of S adding up to T, and on the other hand, if there's a subset of T which adds a subset of S which adds up to T, then the formula is satisfiable. Okay, so we need to have both sides of these implications. Yeah. Okay. So then, so now we're going to do the reduction. Okay. So we're going to start from a formula phi. Okay. So the formula phi is going to so let's assume it's got n variables, x1 up to xn, and it has k clauses, c1 up to ck. Okay. Remember the formula is going to be an and of all of these clauses, right? And then each clause is going to be an or of 3 literals, right? Where literal is either a variable xi or the negation, not xi. Okay, so then we start from one of these formulas, and we can assume that there's no clause that has both a variable and its negation. Okay, because if you have such a clause, then the clause is automatically satisfied, right? Because you're doing an or of x and not x, so that's automatically satisfied. Okay, so if you have such a clause, we'll just take it out of our formula. So then we can assume that our formula does not have any such clauses. Okay, so this is just like a useful technical condition later on for the reduction. Okay. Oops. Okay, so then let me just show you. Yeah, so I'll bring up the picture now. Okay, so what we're going to do is if you have n variables and k clauses, okay, then we're going to create a set of numbers s. And the set s is going to have 2n plus 2k numbers. Okay, so yeah, you take the number of variables plus the number of clauses times 2. That's how many numbers we have in the set. Okay, yeah, so in fact there are two numbers for each variable and 2 numbers for each clause. And furthermore, these numbers are pretty big. Okay, so in fact they have n plus k digits. Okay. And n here is going to correspond, so there's basically one of these digits for each variable, right? You have n variables, and we have and n out of these total digits corresponds to those variables. And then k out of those digits corresponds to the clauses. Okay. And furthermore, all of our numbers are going to be in base 10. Okay, so then, now I'm going to tell you how to create these numbers. Okay, so for each variable xi, okay, we're going to create 2 numbers, vi and vi prime. Okay, And these numbers are going to be that, both the vi and the vi prime correspond to xi. Okay, and so they're going to have a 1 in xi's digit and zeros in all the other digits. Okay, so let's do an example here. Oh, sorry. Wait, 1 second. Right. Yeah. Okay, so let's do an example. Why is this like that? Right. Right. Well, 1 second, guys. Okay, make it. Okay. So the example is, suppose you have a formula like this. Okay, you've got this formula has 4 clauses. Okay, and so for each of these variables, we're going to make 2 numbers, vi and vi prime. Okay, so so you see that in total there are 3 different variables: x1, x2, x3. Okay, and so the numbers are going to have 7 digits, right? Because you have 3 variables and 4 clauses, so we're going to make 7-digit numbers. Okay, and for each of these variables, we're going to make 2 numbers. Okay, so for x1 you have v1 v1 prime. For x2 you have v2 v2 prime, and so on. Okay, and then right, I can't even erase this for some reason. Okay, all right, and then for v1, right, you're going to have a 1 in the x1 digit, right? So this is going to be the x1 digit. Okay, so both v1 and v1 prime are going to have 1s in the x1 digit. Okay, and v2 and v2 prime are going to have 1s in the x2 digit. Okay, and then v3 and v3 prime are going to have 1s in the x3 digit. Okay, all right. So that's part of these numbers. Okay, so we're not done with this entire number yet, right? So we've put a 1 in this place. Okay, but we're going to add some more 1s to this number, to these numbers. Yeah. Okay. So the next part is that if right. Okay. So if a variable, okay, so if this positive literal xi appears in a clause, okay, then the appears in clause j, then the jth clause digit in vi is going to be 1. Okay, so for example, v1, right, v1 or x1, the positive literal x1 occurs in clause 1. Okay, so therefore we're going to take this v1 here is going to correspond to the positive literal x1. Okay, and because it appears in clause 1, we're going to put a 1 in this digit. Okay. On the other hand, if a negative literal occurs, negative xi literal occurs in clause cj, then the jth clause digit in vi prime is going to be 1. Okay, so for example, we have negative x2. Okay, this also appears in clause c1, right? So v2 prime here is going to correspond to negative x2, right? v2 corresponds to positive x2, and v2 prime corresponds to negative x2. Okay, and because negative x2 appears in c1, then we're going to put a 1 for v2 prime in its c1th digit. Okay, so again, this corresponds to negative x2, and because negative x2 occurs in c1, then we're going to put a 1 in v2 prime's c1 digit. Okay, and finally, negative x3 appears in c1, right, in clause 1. So again, we're going to take this v3 prime here corresponds to negative x3, and we're going to put a 1 in the c1 clause, in the c1 digit. Okay. All right, let's do one more example here. So let's take something like, let's take, which one? Let's take this one, okay? All right, so this here is going to be the third clause, right? This is C3 over here. And because negative x2 appears in C3, then we're going to go to v2 prime, and this corresponds to negative x2, right? And because it appears in C3, we're going to put a 1 in that digit. Okay. Also, you see that negative x2 occurs in C2, in clause 2. Okay. So then in the C2 digit, we're also going to put a 1. Okay. So basically, these vi and vi prime, okay, they correspond to xi and xi prime. And for vi, you're going to put a 1 in the xi digit. And then anytime xi appears, the positive literal appears in a clause. Okay, you're going to put a 1 in that digit, in the digit for that clause. So V1 appears positively in C1 and C4, so we're going to put a 1 in those clause digits. Okay, V1 prime, which corresponds to negative x1, right? This occurs in C2 and C3, so therefore you're going to put a 1 in the C2 and the C3 digits. Okay, so that's how we're building these numbers. Any questions about this? Okay, so yeah, so that is going to produce two n numbers, right? So that's going to be so you notice that so these are the numbers that we're building. Okay, yeah, sorry, maybe I should have said this. So this is so each of these rows is going to be one number. Okay, and all of them together is going to be the set S. Okay. So far we've built 2 times n numbers, right? Because we have n variables, and for each one we have two numbers. And then after that, we're going to have 2k more numbers, okay, which are going to be these S numbers. Oh, right, and the other the digits that you do not set to 1, all of them are going to be zeros. Okay, so either a digit is 0 or it's going to be 1. Okay, and then for these S numbers, okay, so they're going to be 2k, so there are 2n of these things, and there are 2k of these things. So for the S numbers, they're just going to have a, so for each clause, okay, we're going to have 2 S numbers, Si and Si prime, okay? And then Si is going to just have a 1 in that clause digit, okay? So for C1, you have S1 and S1 prime, and S1 has a 1 in the C1 digit, and S1 prime has a 2 in the C1 digit, okay? And all the other digits are 0, okay? Likewise, you have C2, right? So C2 is going to have S2 and S2 prime, and they're going to be 1 and 2 in the C2 digit, and then zeros everywhere else. Okay? Yeah. So you see that these are all the digits that you have for the S numbers. Okay? So you have 2 S numbers for each clause. Okay, so those are all the numbers in S that we have. Okay, and the final thing is that we need to specify the target value t. Okay, so this is the target value over here, and the target value is just going to be 1 in all of the variable digits. Right, so these are the variable digits, and then these are the clause digits. So it's going to be 1 in all the variable digits, and then 4s in all the clause digits. Okay, so that's the entire construction. So this is you know, if this is the first time you see it, it might seem like a very bizarre construction. Okay? But we're going to see why this construction actually works and can prove the reduction. Okay, so what we need to do is that we need to show if you have a satisfiable formula, right, then this set of numbers plus the target value is a satisfiable instance of subset sum. Okay, so that's the first part we need to do. And to do this, let's see. Yeah. So assume there is some sort of satisfying assignment row to phi, right? Phi is satisfiable. So let's take some satisfying assignment row. Okay. So we're going to use this assignment to find a subset S prime of S, which is going to add up to T. Okay. We're going to use this assignment to help us find the subset. And the way we're going to do that is, so this assignment is just assigning truth values to each variable. Okay, so if the ith variable is assigned true in row, okay, then we're going to include vi. Okay, we're going to include the value vi in S prime in the set in this subset here. Okay. And if xi is assigned false, then we're going to include the number vi prime in S prime. Okay, so this is part of our S prime, right? So we're either going to include, so notice that you either include VI or VI prime, right? You're not going to include both because XI is either true or false, okay? Okay, all right, okay, so at this point, so this is not the entire set S prime yet, okay? This is just part of S prime, okay? But let's prove some properties about this part of S prime, okay? Okay, so what we can show is that any variable digit. So we want the set S prime that we choose eventually. We want it to add up to t, right? So what we need to do is to ensure that all of these variable digits, okay, these have to add up to t, to this part of t. Okay. So what you can show is that any variable digit adds up to 1. Okay, and this is because you're either going to choose vi or vi prime to be in S, but not both, right? Because xi is either true or false. Okay, so you notice that vi and vi prime, right? They exactly have they both have a 1 in the ith digit, in the digit corresponding to xi. Okay, so if you just choose one of them, right, and not the other one. Oh, right. So that's part of it. Okay, so vi and vi prime both have a 1 in the ith digit. Okay, and all of the other vi's, they all have zeros in the ith digit. Okay, and so because you're either going to choose a vi or vi prime, right? You're only going to choose one of them. Then this is going to produce the 1 in the t. Okay, so as an example of this, we have this expression over here, right? This is going to be our formula. And suppose so we have a satisfying assignment, let's say false, false, true. Okay, so if you plug false, false, true into here, you're going to see that every clause is satisfied. Okay, and so using this assignment false, false, true, we're going to select some of these numbers to include. Okay, so because x1 is set to false, then we're going to include vi prime, the v1 prime in S. Okay, so in fact, you see that all of these lightly shaded numbers, okay, so this one's lightly shaded, and this one, we're going to include all of those, okay? And you see that when you include this, right, then if you look at any of these variable digits, right, for example, this one, then because you only included v1 prime and not v1, then this thing, if you add up this digit, it's going to add up to 1, okay? Likewise, for the x2 digit, if you add up all of the digits here, you see that because you just included v2 prime, right, you get a 1 here. Okay, and then the same thing for the x3 digit. Okay, you get a 1 through this guy. Okay, so that shows claim 1, which is that all of these variable digits add up to 1. Okay, we're trying to make the S add up to this t number. And so we've succeeded partially, right? We've succeeded in this part of t. Okay, but we need to keep going because we might need to add some more things to S. Okay, so also the claim is that after you select, after you select these things to be included in S prime, okay, then every clause digit Cj is going to sum up to at least 1. Okay, and the reason is that, well, first of all, as an example of this, okay, so let's say this clause digit, okay, so now we selected, these 3 things. So if you sum up on this column over here, right, then you see that you have a 1 over here, okay, so this sums up to at least 1 so far, okay, and then if you look at this column, right, then because we selected, we selected these 2 digits, then so far, the things that we selected, right, they add up to more than 1, or to at least 1, okay? And then same thing for C3, right? So these guys actually add up to 3 over here, right? And then this one adds up to 1. Okay, so so the claim is that any clause digit sums up to 1, okay? And the reason this is true is because this row here is a satisfying assignment, okay? And so that means that any clause must have a true literal in row, right? That's the only way that you can satisfy the entire formula is for every clause to be satisfied. And to satisfy a clause, you have to have at least 1 true literal. Okay, so if that literal is a positive literal, okay, let's say xi, okay, then then the way that we then the way that you constructed S prime, right, when xi is positive, when xi is true, then you included vi in S prime. Okay, and now because vi has a 1 in the clause digit cj, right? So here you have a clause cj which is satisfied. Okay, and who satisfied cj? Okay, well, it was a positive literal xi. Okay, And if it's a and so that means that this positive literal so this positive literal occurs in the clause CJ, right? And so that means that because this VI here corresponds to the positive literal, then by our construction, we put a 1 in the clause digit CJ. Okay, so for example, let's see, which one is positive here? Okay, so this one is a positive literal. Okay, and you see that the positive literal occurs in clauses C3 and C4. Okay, and so this V3 here allowed us to satisfy this C3 clause 4 and clause 3. Okay, and you see that because V3 occurs positively in C3 and C4, we put a 1 in those digits. Okay, so therefore, in the in the C3 digit, you have a 1 for this V3 number that you selected. Okay, and that means that the sum on the CJ digit has to be at least 1. Okay, now on the other hand, if the literal that satisfied CJ, right, if this was a negative, negative xi, okay, then we set xi to be false in row. Right? If you look at how we set, well, actually, we included vi prime. Okay. So then, so then we included vi prime in s prime. Okay. So if this literal negative xi satisfies the clause CJ, right, then xi has to be false, right? Because if xi is true, then negative xi is false, and it would not satisfy the clause CJ. Okay. So therefore, xi has to be false, and when xi is false, we included vi prime in s prime. Okay. And you can see that vi prime is going to have a 1 digit in 1 in the clause digit CJ. Again, by how we constructed things. Okay. So for example, if you look at v2 prime over here, right? So this occurs negatively in C1, C2, and C3. Right? So you have negative x2 in C1, C2, C3, right? And because we have this v2 prime here, then this means that we set x2 to false. Okay, so that's why we included v2 prime. Okay. And so by including v2 prime, you're going to make the digits for the sum for digits C1, C2, and C3 be at least 1. Okay, any questions about this so far? Okay, so okay, and the final and one more claim is that currently, based on our S prime, any clause digit sums up to at most 3. Okay, because so far we've selected these 3 numbers. Okay, and you see that when you add up their any of the clause digits using these 3 numbers. Right? So here you've got a sum of 1, here you got a sum of 2, here you have a sum of 3, right? And then here you have a sum of 1. Okay. So all of these things add up to at most 3. Okay. And the reason is just because that the clause J, it includes 3 literals. Okay. So so whichever literals it has, right? So for example, C2, okay, it's got literals negative x1, right? So C2, okay, it's got negative x1, negative x2, and negative x3. Okay. Now we selected negative x1, negative x2, and positive x3. Okay. So when you select, so when you select the literal that occurs in this clause, you get a 1. Okay. And in our case, we only selected 2 of the literals which occur in clause C2. So our sum currently is 2. Okay. If you select only one of the literals which occurs in the clause, then your sum will be 1. Okay? And because there are at most 3 literals in each clause, then your sum is at most 3. Oops. Okay, and so now so now if you put together claims 2 and 3, you see that each clause digit currently sums up to between 1 to 3. Okay. And so, however, what we want is for the clause digits to sum up to 4. Okay, so how do you make them sum up to 4? Well, now we're going to start using some of these S numbers. Okay, so previously we only used the V numbers, right? But now we're going to start using the S numbers, okay? And we're going to use them in order to get the entire sum in each of these clause digits. We want that entire sum to be 4, okay? So what we're going to do is if you have a clause digit where the current sum is 1, okay? So for example, in C1, the current sum is 1, right? In C4, the current sum is 1, okay? Then we're going to since you want the sum to be 4, then we're going to add 3 more to this. Okay. So then how can you add 3 more to, for example, this digit? Well, we created 2 of these S numbers, which are 1 and 2 exactly in the C1 digit. And there's zeros everywhere else. Okay. So if you include both of them, right, then now your sum in the C1 column is going to be, C1 digit is going to be 1 plus 1 plus 2, and it's going to be 4. Okay. Likewise, if you look at C4, the sum is currently 1. Okay. But since you want the sum to be 4, then we're going to use these S4 numbers. Right. We have 2 S numbers exactly corresponding to clause 4. And if you add both of them, then you increase the sum by 3, and you get the sum up to 4. Okay. On the other hand, if you look at a different different clause digit. Okay. So for example, for C2, the sum currently is 2. Okay. So therefore, we only need to increase the sum by 2 more. Okay. So then we're going to look at these 2 S numbers. We're going to look at S2 and S2 prime, and we're only going to include S2 prime. Okay. Because S2 prime has 2 over here, and if you add it to the other 2, you get 4. And then lastly, for C3 over here, the sum is already 3. So you just want to add 1 more to that digit. Okay, so we're going to look at these 2 numbers corresponding to C3, and you're only going to add S3, which is 1 in that digit. Okay, right. So this is how we choose all these numbers. Okay, so the numbers, so we're going to choose them in two steps. Right. In the first step, we're going to look at you're going to look at your satisfying assignment row, right? And for each variable, if it's true, you're going to include, if xi is true, you're going to include vi. And if xi is false, you're going to include vi prime. So that's how we chose these 3 numbers up here. Okay. And after you choose those 3 numbers, what you achieve is that for all of these variable digits, they add up to exactly 1. And for the clause digits, they add up to somewhere between 1 to 3. Okay. And so in order for the clause digits to add up to 4, we're going to choose some more of these S numbers. Okay, and so, right, yeah. Okay, so any questions about how we do this? So what this shows is that, if you have if there exists a satisfying assignment, right, then you can choose a subset of these numbers that we have, such that they add up to exactly t. Okay, so we've proven this implication. Any questions about this part? Okay, right, so then let's continue. So then now we need to do the other proof direction, okay, which is that if you have a subset of numbers which adds up to t, then you can find a satisfying assignment. Okay, all right, so let's assume that there is a subset S prime which adds up to t. Okay, so we're going to use this S prime to somehow produce a satisfying assignment, phi. Sorry, the satisfying assignment is called rho. Okay. All right, now, okay, so the first thing is that if you look at any digit, okay, so when you have this subset, right, if you look at any digit, it's going to add up to at most 6, okay, and that's because, if you look at any of these digits, okay, this one, this one, this one, and so on, right, you see that, if it's one of these variable digits, then it can add up to at most 2, okay, oh, I can't write, okay, anyways, it can add up to at most 2, okay. And if it's one of these clause digits, right, then you have 3 of these, you have 3 ones corresponding to the literals, and then you have 2 more numbers, which are 1 and 2. Okay, so at most you get a sum of 6. Okay. And so the point here is that because things can add up to at most 6, then when you take any of these numbers, any subset of these numbers, okay, and you add them together, there are no carries. Okay, meaning that so you get a carry if the sum in a digit is more than 10, then you get a carry to the next digit. Right? But because we know that for each of these digits the sum is at most 6, then there are never any carries. Okay, right. So now we're gonna start producing our satisfying assignment. Okay. So what we know is that because S prime adds up to 1 in the variable digits, okay, then either VI or VI prime is going to be included in S prime, but not both, right? So for example, if you look at this digit, okay, you can only include either this number, right, or this number, but you cannot include both of them, because if you include both of them, the sum is going to be 2, okay, and you have to include one of them because otherwise, because you have a sum of 1 here, and if you do not include either of them, right, if you then your sum is going to be 0. Okay, yeah. So that means that for any for the set S prime, okay, for each of these variables, right, for x1, x2, and x3, you're only going to include either VI or VI prime. Okay, but not both. And so this means that so now we can use this to generate a satisfying assignment. Okay, because if we included VI in S prime, then we're going to set xi to be true. And if you included VI prime, you're going to set xi to be false. Okay, so this is going to be our assignment. Okay, this is how we assign truth values to all of these variables. Okay. If VI is an S prime, then you set the variable xi to be true. And if VI prime is an S prime, you set variable xi to be false. Okay, so we're going to call this assignment rho. Now, the first thing is that rho is a valid assignment, okay? Meaning that either you made xi true or xi false, but you didn't try to make them both true and false, right? Because, because you see that, because we said that either VI is an S prime or VI prime is an S prime, okay? And only one of these happens. And so xi is either set to true or false, but not both. Okay. So now we've shown that rho is valid, but you also need to show that rho satisfies this formula phi that you have. Okay, so how do you do that? So consider any clause Ci or Cj. Okay, so we want to show that Cj is satisfied using our assignment rho. Okay, so for example, let's consider this C1 over here. Okay, now C1. So what we know is that if you look at the S digits corresponding to C1, okay, so these two digits, okay, so at most they add up to 3, right? Because you have two S numbers corresponding to C1, okay, and in the C1 digit they add up to at most 3. However, because C1 in total adds up to 4, right? The C1 digit in total adds up to 4. Then that means that among these variable numbers, right? So these numbers correspond to the variables, right? The V numbers correspond to the variables, right? We must have included one of them in our set S prime, right? We have to include one of these variable numbers in S prime, because if you don't include any of them, then the sum in the C1 digit is only going to be 3, right? It's at most 3, and we know the sum is actually 4. So we know that we must have included one of these variable numbers. Okay? And so in fact, you see that in this case, we included this variable number over here. Right? Oh, I'm sorry, let me erase this. We included this variable number over here. Okay. And okay, so so if this variable number is a so this variable number is either like VI or VI prime. Okay, so in this case, it's it's V2 prime, right? And that means that so because this V2 prime number is a 1 in the C1 digit, okay, then this means that negative x2 actually occurred in clause C1, right? You see that negative x2 actually occurred in clause C1. And the reason is because the way that you built these numbers, okay, these VI and VI prime numbers, is that if you have a 1 in the clause digit Cj, okay, then that means that this literal actually occurs in that clause. So here you have this literal corresponding to negative x2, right? And because it's 1 in the C1 digit, then this means that negative x2 actually occurs in clause C1. Okay. All right. As another example, if you look at right. Okay. Right. So let's finish up this. So we know that this negative x2. Okay. This actually occurs in this clause C1. Okay. And the way that we set our assignment was that if negative x2, if you include v2 prime, right, then you're going to set x2 to false. Right. That's how we set our. That's how we did our assignment. Okay. If you include vi prime, you're going to set xi to false. Okay. So therefore, in our assignment, we set x2 to false. Okay. And if you set x2 to false, right, then because negative x2 occurs in clause C1, then if you set x2 to false, you're going to satisfy this clause C1. Okay, so what we've shown is that, first of all, there has to be one of these, so for each clause, for clause C1, okay, there has to be a number which is 1. We must have selected a number which is 1 in this clause digit. Okay, and if you and whichever literal that corresponds to, okay, so whichever row you selected, that corresponds to a literal. Okay, and the way that you set this literal, right, for example, this x2 here, okay, we set x2 to false, and when you do that, you're going to end up satisfying this this clause. Okay, so whenever you have a 1 in this clause, right, then the literal that you that corresponds to that, for that clause is going to make the clause be satisfied. Okay, so let's do another example here. So for example, if you take this digit C2 over here, right? So C2, what you see is that C2, you only selected S2 prime here. Okay, so that means that for the variable numbers, you have to select 2 of them. Okay, because in total you need things to add up to 4, and for the clause numbers, it only adds up to 2 in the C2 digit. Okay, so what we see is that we selected we selected exactly 2 of these variable numbers. Okay, and for each of these variable numbers, right? So you selected v2 prime and v1 prime, and that means that you set so this implies that you set x1 to be false. Right, because you selected v1 prime, and you set x2 to be false, okay, because you selected v2 prime. And also because in the v1 prime number you have a 1 in the C2 digit, then this means that negative x1 actually occurs in clause 2. Okay. Likewise, you have v2 prime has a 1 in the C2 digit, and that means that negative x2 occurs in clause 2. Okay? And since we set both of these variables to be false, then because negative of that variable occurs in clause C2, then clause C2 becomes satisfied. Okay? Yeah. So so the upshot is that like in summary, what's happening is that for each of these variable digits, okay, let's say for C4, okay, we're guaranteed that you must have selected one of these variable numbers that corresponds to this digit. Okay, that corresponds to C4, for example. Okay, we selected this v3 over here, and when you select this one, then the way that we set these truth values, right, you're going to set this x3 here to be true. And we also know that x3 actually occurs, the literal x3 occurs in C4, right? The literal x3 occurs in C4. And so when you set x3 to be true, you satisfy the clause. And this holds for every clause. Okay, so every clause you can find the way that we set our literals, you're going to satisfy that clause. Okay, yeah, so in this way, all of the clauses are satisfied. Okay, and this shows that phi is overall satisfied, right? Because we gave this assignment rho, which satisfies all of phi. Okay, any questions about this? Okay, so I'm going to say a few more things and then we'll take a short break. Okay, so all right, so first of all, our reduction runs in polynomial time. Okay, because we construct this total number of values, and then each one of them has that many digits. Okay, yeah. So this is a polynomial time reduction, and this shows that 3CNF reduces to subset sum, and so subset sum is NP complete. Okay. Now, I just want to mention one thing, which is that we actually earlier we gave a dynamic program to solve subset sum. Okay, so if that dynamic program actually ran in polynomial time, then because subset sum is NP complete, this would actually show that we have a polynomial time algorithm for an NP complete problem, and that would mean that P equals NP. Okay, that would be incredible, right? And so did we actually prove that P equals NP? Okay, well, unfortunately, we did not prove that P equals NP. Okay, because remember the dynamic program that we gave, the running time for that algorithm is n, where n is a number of values, right? It's a size of the set S. Okay, times w, where w is the largest value in S. Okay, so it's not the so w here is like the largest number, which is actually in S. Okay. However, this running time, okay, this is not a polynomial running time in the input size, okay, because the input size is that we have n numbers, and then if the maximum value is size w, then the number of bits, the size of the input to represent that number is actually log w. Okay, so for example, if you have numbers like 1 and then 10 and then 1,000, or 100, okay, and let's say 1,000, okay. So here you have 4 numbers, right? And the total number of bits that you need to represent it is we need 10 digits over here, right? 1, 2, 3, 4, okay? We need 10 digits. So our input size is basically 10, okay? However, your input value, okay, this W over here is actually 1,000. So therefore, the running time of that algorithm was like n times 1,000, not n times 10. Yeah, so therefore, this previous algorithm is not a polynomial time algorithm. Okay, it's a so-called pseudo-polynomial time algorithm, where pseudo-polynomial means that the running time is polynomial in the value of the input, not the size of the input. Okay, so our running time is actually polynomial in the value w of the input, but it's not polynomial in the size of the input, which is log w. Okay. All right. Yeah. So. So therefore we still do not have a polynomial time algorithm for this NP complete problem. Okay. All right. Any questions about anything? All right. So then let's take a break to like what time is it? It's to 11:10. Okay. So we'll come back in about 7 minutes, and then we'll do some more reductions. Okay, so we're going to continue with the lecture. All right, and then we're going to do a few more reductions. Okay, so right, so the next problem we're going to show is NP complete is Hamiltonian cycle. Okay. So so the problem is that you're given a graph, okay, like this graph over here, and then the question is whether you can find a cycle which goes through all of the nodes in the graph exactly once. Okay, so the cycle needs to start and end at the same node. Right? And furthermore, it needs to go through every node exactly once. Okay, so for example, in this graph, there is a Hamiltonian cycle. Okay, if you just follow these blue edges, right, you see that you start and end at the same place, and you go through every node exactly once. Okay. On the other hand, there are some graphs where you cannot find a Hamiltonian cycle. Okay, no matter how you go through the graph. Right? If you start and end at the same place, you either do not go through all the nodes, or you have to go through some nodes more than once. Okay. So for example, if you have a bipartite graph with an odd number of nodes, okay, then it turns out that there are no Hamiltonian cycles in this graph. Okay, so you can sort of think about why that is. Okay, so try to convince yourself that this is true. Okay, you can start with like a small bipartite graph with an odd number of nodes, and you can easily see that there are no Hamiltonian cycles, and then you can try to prove this fact for all such graphs. Okay, now before I go on with this, I just want to mention that there's another problem which is quite similar to Hamiltonian cycle. Okay, but it's also very different in some ways. Okay, and that problem is called Eulerian cycle. Okay, so so basically for the Euler cycles, right? So this is we're trying to find Euler cycles. Oops. So there, what you're trying to do is you're given a graph and you want to go through every edge exactly once. Okay, so for Hamiltonian cycle, you want to go through every node exactly once. And for Euler cycles, you want to go through every edge exactly once. Okay. Now, so for example, if you have a graph like this, okay, then you can go through every edge exactly once. Okay, you just go to you just go like sort of around the pentagon, right? And then you oops, let me do it again. All right, you go around the pentagon, right? And then you go like that, okay? And there you go through every edge exactly once. Okay. So so this problem is actually easy to solve. Okay, there are polynomial time algorithms for this. In fact, there's a theorem which says that if you look at if you're given a graph and you look at the degree of each node, okay, if all of those degrees are even, so there exists an Eulerian cycle for a graph if and only if the degrees of every node are even. Okay, so for example, for this graph, you have that all the degrees here are 4, right? So this guarantees that there is an Eulerian cycle. Okay. If you have another graph where this is not true, then you do not, then you won't have an Euler cycle. Okay, so this problem, the Eulerian cycle, is actually solvable in polynomial time. Whereas for the Hamiltonian cycle, we're going to show that this problem is NP complete. And to do this, we're going to use a reduction, and again, we're going to use SAT to reduce to Hamiltonian cycle. Okay. So in fact, we're going to look at directed Hamiltonian cycle. So this means that you're given a directed graph, and you want to find a cycle in this graph which goes through all the nodes exactly once. Okay. But it turns out that undirected Hamiltonian cycle is also NP complete. Okay. It's a bit more complicated to prove, but it's also true. Okay, but we're going to do it for the directed problem. So what we're going to do is we're going to start with an instance phi of 3 sat. Okay, and then we're going to construct a graph where this graph has a directed Hamiltonian cycle if and only if phi is satisfiable. Okay, so so the way we're going to build this graph is that we're going to build it in 2 parts. Okay. So, so suppose your 3-sat instance phi has n variables and k clauses. Okay. So we're first going to build part of the graph which corresponds to these variables. Okay. So the way that we're going to do this is we're going to have so this graph is going to have like layers. Okay, we're going to have one layer for each variable, and how many nodes are? Oh, right. So I'll say later how many nodes are in each layer. Okay, but basically you see that suppose you have a formula with like 3 variables. Okay, then you're gonna make 3 layers in this graph. Okay, and the layers are going to be such that you can go through this layer in either direction. Okay, so for each layer you have all of these bidirectional links. Okay. And furthermore, you can go from, so we're going to number all of the variables, let's say x1 up to xn, okay? And you have edges from xi to xj, okay? So you can either go, so for each variable, you have edges from xi to xj, xi to xi plus 1, okay? So you only have edges between consecutive layers, okay? And you can go to the next layer either from the sides, right, like these edges over here, right? Or you can go across like this, okay? And those are the only ways to get from one layer to the next layer, okay? You see that these edges are directed edges, okay? Yeah, and so in this graph, you see that there's no way to go sort of upwards, okay? You can only go downwards in this graph, right? You can take one of these zigzag paths downwards, but, sorry, let me erase this, okay? So you can only take these downwards edges, right? You can take a cross edge, which takes you sort of across the graph like this, right? But you see that there are no edges which go up, okay? You can never go up in this graph. Okay, what else? Okay, we're also going to add 2 additional nodes, okay? This S node and the T node, okay? And the S node is going to, so the S node is going to have 2 edges to the left and right sides of the X1 layer. Okay, and the T is going to have it's going to have these 2 edges. Okay, from the final layer corresponding to Xn, we're going to have 2 edges to T. Okay. And then lastly, you have this edge from from T back to S. Okay. And also the number of nodes in each layer is going to be 3k plus 3, where k is a number of clauses. Okay, now if you look at this graph, so let's first of all look at the Hamiltonian cycles in this graph. Okay, so basically, the only Hamiltonian cycles are, since we saw that you can only go downwards in this graph, okay, so you can either have a Hamiltonian cycle kind of like this, right, you can just wrap around this entire thing, right, or as you're going down this graph, you can actually zigzag back and forth, right, you can go from the left to the right, to the left to the right, right, so if you have many of these layers, you can go like in a zigzag fashion. Okay, but in the end, you have to go back to the beginning. Okay, or you can you can go downwards for a few layers, right, and then you can zigzag for a while, and then you can go downwards for a few more layers. Okay. But basically, you can see that the only Hamiltonian cycles you have are the ones that either for each layer you can either go down from the you can either go down from the left side or the right side. Okay, and when you switch, you have to take one of these zigzag paths to switch sides. Okay, yeah, so that basically corresponds to each variable. Since you're either going to go down from the left side or the right side, this is going to correspond to whether we set the variable to be true or false. Okay, so I haven't constructed this entire graph yet. Okay, but up to now, the intuition that you should have for the current construction is that when you take a zigzag path, right, this corresponds to an assignment of truth values to all of these variables, right? Because each of these layers corresponds to a variable, okay? And if you go from the left, that corresponds to setting the variable to be true, and if you go from the right, it corresponds to setting it to false. Okay, so that okay. So next, we need to continue with this construction, okay? Because currently we've added a bunch of nodes corresponding to the variables, okay? But we haven't added any nodes corresponding to the clauses yet, and we need to do that, okay? So what we're going to do next is that we have these k clauses, okay? And for each clause, for each clause, we're going to make one node. Okay, so in this example, we have 2 clauses, C1 and C2, and we're going to make 2 nodes, okay, corresponding to those clauses. And for each of these clauses, you're going to have 6 edges for that clause node. Okay, and the way that you set the edges is that in the clause, you look at each literal. Okay, so if it's a positive literal, then what you're going to do is you're going to look at this graph from left to right, okay? And then, right, and yeah, so we're going to reserve some of these nodes in each layer for this clause, okay? And for those nodes, so we're going to reserve two nodes for each of these literals in the clause, okay? And so if it's a positive literal, okay, then you're going to set the then the way you're going to add the edges is that for the left node, okay, so we're going to reserve these two nodes, let's call it the left and the right node, okay. So the left node is going to go up to this clause node, okay, and then the right node is going to come down from the clause node, okay. So you see that you have an up thing and then you come down like that, okay. This is for the positive literals, okay. On the other hand, when you have a negative literal, okay, so for example, here you have a negative literal, right? So, oh wait, I'm sorry, I did that wrong. Okay, sorry, let me just go back. I did something wrong. Okay, so for x1, okay, this is we're gonna make some edges from this layer for x1. Okay, so here you have a layer of nodes corresponding to variable x1, and so for this literal x1 over here, because it's positive, right, we're going to reserve two nodes in this x1 layer for this literal, and the two nodes are going to go up, right? So the left node is going to go up, and the right node is going to come down like that. Okay, right. And for another literal, let's say this one that occurs negatively, right? So we're again going to reserve two nodes in the x2 layer for this literal, okay? But now if you look at the left-right nodes, right? So the right node is going to go up, and the left node is going to go down. Okay, so the difference is when it's a positive literal, right? The left node goes up, right? Goes up, right? And the right node comes down. Okay, and when it's a negative literal, right? The left node comes down, and the right node goes up. Sorry, the right edge. Okay, the edge from the right node goes up. Okay, and then lastly for x3, because it's a positive literal, right? So then in the x3 layer, right, we have two nodes. Oops, we have two nodes like this, and because it's a positive literal, the left one is going to go up, and the right one is going to come down. Okay, does that make sense? Okay, and we do this for every clause. Okay, so every clause is going to have its own reserved nodes. That's right. Yeah, every clause has its own reserved nodes, and for each literal in the clause, you reserve two nodes. Okay, so for this clause 2, right, we're going to reserve two nodes for the first literal in the x1 layer. Okay, and these two nodes are going to be different from these two nodes, which were for x1 in clause 1. Okay, and also because so we have the left and the right node, and because x1 here occurs negatively in C2, okay, then the left one is going to come down and the right one goes up. Okay, all right, yeah. So we're gonna again, when you have k clauses in total, you're gonna construct k of these clause nodes. Okay, and then for each clause node, you're gonna add 6 edges. Right, you add 2 edges for each literal. Okay, and so each literal is going to correspond to some some disjoint set of nodes in the so a literal xi the literal for the variable xi is going to have 2 reserved nodes in layer I. Okay, and either of these nodes are going to go up and down or down and up. Okay, so that is the construction. Okay, so now we're going to show that this construction is correct. Okay, so we're going to show that if phi is satisfiable, so the first direction is that if the formula is satisfiable, then there is a Hamiltonian cycle. Okay, so yeah, so if the formula is satisfiable, then what we're going to do is we're going to take a satisfying assignment, x star here. Okay, and if the ith variable is true in x star, okay, then so we're going to use x star to construct a Hamiltonian cycle. And what we saw for the Hamiltonian cycles for this graph was that you basically have to start at S, right? And then you're going to zigzag in this graph, and then eventually you're going to go back to S, okay? And then you're going to go to T and then back to S, okay? And so as you traverse this Hamiltonian cycle, you're either going from left to right, or you're going from right to left, okay? Yeah, so, right. Okay, so what we're going to do is if xi is set to 1, okay, in this satisfying assignment, then you're going to traverse row I from left to right. And if xi is set to 0, then you're going to traverse it from right to left. Okay, and yeah, and we claim that if you do this kind of traversal, then you can actually go through all of the nodes. Okay, so for example, yeah, let's. All right, so for example, for this graph, okay, so one satisfying assignment is, what is it? Let's say we can make things true, true, false, okay, so x1 equals true, x2 equals true, and then x3 equals false, okay? So then this is going to satisfy clause 1 here, and then it's also going to satisfy clause 2 over here, okay? And so because the satisfying assignment is true, true, false, then we're going to go through the layers in so here this is going to be a left to right traversal, this is going to be left right, and this is going to be right right left. Okay, and so the way this is going to work is that, let me erase this. Okay, so we're going to start at S. Okay, and then first we want to go through x1 layer from left to right, so we're going to go like this. Okay, and then next we want to go through the x2 layer from left to right, so we're going to go again like this. Okay, and then finally we want to go through the x3 layer from right to left, so we're going to go like this. Okay, and then we're going to go to T and then back to S. Okay, all right, sorry, let me fix this up a little bit. Okay, all right. However, we're not quite done yet, okay, because this path that I drew over here, okay, this goes through almost all of the nodes. However, it did not go through any of these clause nodes, right? You see that we only went through these variable nodes over here. We didn't go through the clause nodes, okay? So we need to somehow add in the clause nodes, okay? So how do we add in the clause nodes? Well, because we said, because you're going through x1 from left to right, right? x1 is set to true, and so you go through it from left to right. Then what happens is, as you go through x1 from left to right, okay, you see that you're going to hit this node which corresponds to x1 in clause 1, right? So this these two nodes both correspond to x1 in clause 1, okay? And because x1 occurs positively, then in the left node, right? So here you have a left node and a right node. So the left node is going to go up, and the right node is going to come down. And so because we're coming to this node from the left, we can now go up and we can go down. Okay, and then after this, we can continue all the way to the other side. Okay, so this means that whenever you have a you have a variable which is set to true, you're going to come to this node from the left. Okay. And also, because the variable is set to true, then, if a variable is the satisfying literal in a clause, okay, so the C1 has to have a satisfying literal, for example, x1 here, right? So x1 is a literal which satisfies C1, and if x1 occurs positively, then we set x1 to true, and when you set x1 to true, you're going to come to this x1 node from the left, and then next you can take this up edge to the clause 1 node, and then you can come down from the other edge. Okay. Now on the other hand, what about this clause 2 node? Okay. So here, if you look at this assignment here, right, the one one literal which satisfies C2 is going to be x3. Right, these other ones are both false in this C2, okay? Oops. All right, so x3 here is a positive literal, it's a negative literal, right? And because you set x3 to false, right, then we're going to go through the x3 layer from right to left, right? Okay, so when you go from right to left, you also have that because x3 occurs negatively in clause 2, okay, then the right node actually goes up, right, and the left node comes down. So as you're coming from the right, okay, you're going to hit the right node first, and then you can take the right node up to the C2 node, okay, and then you can come down from the left side, and then you can continue to the other side of x3. Okay, so in summary, when you have a satisfying assignment, right, that tells you which direction you're going to go through all of these layers in. Okay, and for the satisfying assignment, if you look at any clause, it has a literal which satisfies that clause. Right? Otherwise, you wouldn't have a satisfying assignment. Okay, so it has a true literal. So for every clause, there is a true literal. Okay, and if that true literal is a positive literal, right, then you're gonna set that literal to be true in the assignment, and in your Hamiltonian cycle, you're gonna come to that literal from the left. Okay, and furthermore, because of how we added these edges, okay, when you come from the left, there's an edge which takes you up to the clause node, and then you can come down from the other node, from the right node. And on the other hand, if the literal occurs negatively in the clause, okay, then in the satisfying assignment, that variable was set to false. Okay? And when you set the variable to false, you're going to traverse that variable's layer from right to left. Okay? And also, because the literal is false, because it's a negative literal in the clause node, okay, then you have that the right edge goes up, the right edge for the nodes corresponding to that literal, okay, for these two nodes, for example. Okay, the right edge goes up and the left edge comes down. Okay, and so as you traverse this thing from right to left, right, you're going to hit the right node first, and then you're going to go up to the clause node, and then you're going to come down from the left node. Okay, so this shows us that whenever you have a satisfying assignment, right, you can go through all of the nodes exactly once. Okay, because we went through each layer exactly once, right? All of these nodes corresponding to variables, we went through exactly once. And also all of these clause nodes, right? You can also hit these clause nodes as you're going through one of these layers. Okay, so any questions about this part? Okay, so this means that if you have a satisfying assignment, right, and if you go through the nodes in this in these directions, right, and then also whenever you can, you try to also go to the clause nodes. Okay, so as you're going through each of these layers, whenever you hit a variable, which if you're going through a layer, and if this layer corresponds to a literal which satisfies a clause, then you also go up to that clause node. Okay, and in this way, you can go through all of the nodes. And so you have a Hamiltonian cycle when you have a satisfying assignment. Okay, so so that shows one direction of this. Okay, so so the other direction is to show that if you have a if you have a Hamiltonian cycle, then you also have a satisfying assignment. Okay, and so the way this works is that let me just clean this up over here. So if you have a Hamiltonian cycle, then we know that this so this Hamiltonian cycle has to go through things in this zigzag order, in the zigzag fashion, right? In this sort of you can either go through things from the left or the right, but you have to go through in this fashion, because you can see that there's no other way to there are no other Hamiltonian cycles in this graph. Okay. And so now what we're going to do is for each of these layers. Oh, so one thing is that we also have to go through all of the layers in order. Okay, so meaning that your cycle has to first go through the nodes in layer 1, in layer x1, and then layer x2, and then layer x3. Okay, you cannot, for example, go through things in layer, you can't go through x3 first and then layer x2, okay? Because, you can see that if you try to go from x1 to x3 and then back to s2, then you can see that you're gonna be using this node more than once, okay? Right, if you try to come up, if you come up over here, right, you're still gonna have to go all the way across, and so you're gonna end up using using some nodes multiple times if you try to skip any layers. So therefore, your Hamiltonian cycle has to go through all of these layers sequentially, okay? Layer x1, x2, x3, and so on. Okay. And also, when you go through a layer, you have to go all the way through the layer, right? You can't like go halfway through the layer and then decide to like not finish the layer. Okay, because if you try to go back, then you're going to be repeating some of these nodes. Okay, so once you start going through a layer, you're going to have to go through the entire layer. And for each layer, you can either go through the layer from left to right, or you can go from right to left. Okay, so therefore, we have a very fixed structure for how these Hamiltonian cycles look in this graph. Okay, we're going through the layers one by one, and then we either go from the left to right or from right to left. Okay, so then we're going to use this structure to determine our truth assignment for the 3-sat formula. Okay, so what we're going to do is if you go from left to right, okay, so if in the xi layer you go from left to right, then you're going to set xi to be true. Okay, xi is going to be true. And if for the xi layer, if you go from right to left, then you're going to set xi to be false. Okay. All right, and then we claim that this assignment is going to satisfy the 3-sat formula. Okay, so to show this, what we have is that okay, so we need to show that every clause becomes satisfied. Okay. And the reason this is true is because, for example, if you consider this this clause node, okay, so we know that in the Hamiltonian cycle, we must have gone through this clause node at some point, right? Because because you have to go through every node, okay. And there are basically only 3 places where you can get to this clause node. Okay, you can start either here and get to the clause node, right? Or you can start here and get to the clause node, or you can start here and get to the clause node. There are no other edges to this clause node. So the only way that we could have arrived at this clause node in our Hamiltonian cycle is through one of these 3 nodes. Okay. And when you arrive at this Hamiltonian cycle, so if you arrived, right, so if in this Hamiltonian cycle, let's say you were going left to right, okay, so let's see, so actually, no, let's say it's, so we know that one truth assignment is, one satisfying truth assignment is x1 equals true, right, x2 equals, what, let's say it's going to be true, okay, and then let's say x3 is false, okay, so that's going to be one satisfying assignment, okay. Now, suppose we actually had a Hamiltonian cycle where you went through x1. So because x1 is true, we actually want to go through this thing from left to right. Okay? But suppose your Hamiltonian cycle actually went through this x1 layer from right to left. Okay? If it went through the x1 layer from right to left, right, then can it actually arrive at this C1 node? Okay, and the answer is that it cannot arrive at the C1 node, because if you go from right to left, right, then in order to get to the C1 node, you have to go over here, right, and then you can get to the C1 node. Okay, but then next you have to come down through this other node, right, through this other edge. Oops, sorry. Okay, you cannot come down through some other edge, like for example this edge. Because if you come down through this edge, then this means that you did not go all the way through this x1 layer. Okay, and we know that you have to go all the way through the X1 layer, because if you don't go through the X1 layer right now, right, then eventually you have to somehow get to this X1 layer, and at that point, you're going to end up repeating some nodes. Okay, so if you went through the X1 layer from the right to the left, then the only way to get to C1 is you're going to have to take this left node first, right, and then you're going to have to come down through the right node. Okay, but if you come down to the right node, then now you have nowhere to go, right? Because you can't go this way because you've already gone through all of these nodes. Okay, and you also can't go this way because you just went through this node. Okay, so this means that when x1 occurs positively in this clause, then then you could not have arrived at x1 from the right. Okay, you could not have arrived at x1 from the right. Okay, this is impossible. Okay, the only way for you to go through this x1 node, C1 node, is that if you went from the left to the right. Okay, if you went this way. Yeah. Okay. So if you went this way, then you can arrive at C1, right? And then you can come down over here. So and if you go from left to right, then we're going to set xi to be true, right? So you're going to set x1 to be true over here, and we know that x1 is a positive literal in this clause. So if you set it to true, then you're going to end up satisfying this clause. Okay, so so again, the only way to go through one of these clause nodes is to go through it in the right direction. Okay, so if it's a positive literal, if a literal occurs positively in this clause, the only way to get to that clause from, if you got to C1 through x1, and x1 is a positive literal, then you must have come from the left. Okay, alternatively, you could have gotten to C1 through x2. Okay, if you got to C1 through x2, then you have to come from the right. Okay, and that's because if you came from the left, right, then you would have to go like this. Okay, and then you get stuck. Okay. So if you arrived at C1 through x2, right, then you must have come from the right, right? But if you come from the right, then you would set x2 to be false over here. And because x2, because you have a negative x2 literal, then when you set x2 to be false, then you're going to satisfy this C1 clause. Okay, so basically, for this C1 clause, you must have arrived at it through either the x1 layer or the x2 layer or the x3 layer. Okay, if you arrive at it through some layer, and this layer is a positive literal, okay, like x1 or x3, then you must have come from the left. Okay, and when you come from the left, you're going to set this variable to be true. And if you set the variable to be true, then because it's a positive literal, it will make the entire clause be true. Okay, if you arrived at this clause node from a layer where it's a negative literal, okay, then you must have come from the right. Right? And when you come from the right, you're going to set the variable, you're going to set this variable to be false. And so then the literal is going to become true. Okay, so again, you satisfy this clause. So this shows that because we know every clause node is visited in this Hamiltonian cycle, okay, every clause node has to be visited, then we must have arrived at it through one of these layers, and then whichever layer you arrive through, okay, that's gonna cause that variable to be set to either true and false, and that will satisfy this literal. That literal will satisfy this clause. Okay. Okay, so that might be a little bit confusing. Any questions about this? Right, so I'm not sure if I said that clearly. Okay, Okay, so all right, I'll just do one more example just to maybe try to clarify this some more. Okay, so for example, for C2, right, we know that you in the Hamiltonian cycle, you must have arrived at the C2 node somehow, right? You can either arrive it through the X1 layer or the X2 layer or the X3 layer. Okay, now if you arrive at C2, let's say from the X1 layer, okay, you could not have arrived at it from the left. Because if you arrive from the left, you would have to go like this. Okay. So therefore, if you arrive at C2 through the X1 layer, you must have come from the right. Okay. But if you come from the right, then you're going to set X1 to false, right? Because that's what we do here. Okay. If you go from the right to the left, you set the variable to false. And if it's set to false, then it will make this, this negative X1 literal become true. And that will satisfy C2. Okay. Likewise, if you arrived at C2 from the X2 layer, right, that would also cause C2 to become satisfied. And so because we know that we arrived at C2 through one of these layers will cause C2 to be satisfied. And this occurs for every possible clause. Okay, so therefore, every clause becomes satisfied. And that means that if you have a Hamiltonian cycle, then you also have a satisfying assignment. Okay? All right, so now we proved both sides of this reduction, and so that shows that 3-SAT reduces to directed Hamiltonian cycle, and it's NP complete. Okay, so so the last thing is I'll just finish up with another problem. So this time we're going to show this problem is NP complete, but we're not going to use a reduction from 3-SAT, okay? Because this problem is actually very similar to Hamiltonian cycle. So therefore, we're going to use a reduction from Hamiltonian cycle to this problem. Okay, so it just shows you that you don't always have to use 3-SAT for these reductions. Okay, so the problem is this traveling salesman problem. Okay, so imagine that you have a bunch of these points, right? A bunch of these nodes in a graph, and between every pair of nodes, there's some sort of distance. Okay, so for example, from this node to that node, there's some distance, right? From this node to that node, there's some distance. Okay, so between every pair of nodes, you have some distance. Okay, so in this graph, you have like 13,000 nodes, so you have like 13,000 squared number of distances, basically. Okay. And now what you want to do is you want to go through all of these nodes in some way, okay? So you're going to make a path through all of these nodes, and you want the total length of that path to be as small as possible, okay? So for example, if I give you a threshold D, okay, is it possible to go through all of these nodes and to go through each node exactly once? Okay, so you want to go through every node exactly once and have the total path have length less than D. Okay, so for example, if you take this path, okay, this apparently is the smallest way, the shortest way that you can go through all of the nodes exactly once. Okay, so I'm not sure what the length of this is. Let's say it's 1,000. Okay, so if I give you this graph and I ask you, is it possible to go through this graph using total length less than 1,000, then you would say yes. Okay, but if I say, is it possible to go through using length less than 500, then you would say no. Okay, so this is a decision problem for TSP where you're given both the graph and all of these pairwise distances and a target value D. Okay, and it's a yes instance when it is possible to go through all the nodes exactly once using length less than D. And it's a no instance if it's not possible to do that. Okay, so so now this decision version of the TSP problem, okay, this is also, this is NP complete. Okay, so here's another example where you might, here's another example, okay, and this is like the shortest way to go through all of these, all of those nodes. Okay, so now we're going to show that this TSP problem is NP complete. Okay. But we're not going to do a reduction from 3-SAT because, as you can see, these reductions from 3-SAT are kind of complicated. Okay. But because this TSP problem is so similar to Hamiltonian cycle, okay, because for Hamiltonian cycle, you're given a graph, right? It's a directed graph, and it's not a complete graph. Okay, so for Hamiltonian cycle, you don't have a complete graph, right? Because if you have a complete graph, right, then of course you have a Hamiltonian cycle. Okay, so for a Hamiltonian cycle, you just have a some subset of the nodes. Okay, and your question is whether you can go through all these, whether you have a cycle that goes through all the nodes exactly once. Okay. For TSP, you have a complete graph. Ooh, sorry, 1 second. Right, for TSP, you have a complete graph. Okay, but your question is, can I go through all the nodes using a tour of less than some distance? Okay. So they're not the same problem, of course, but they're quite related because they both require this path that goes through all the nodes exactly once. Okay, so now because they're so related, then it's easier to do a reduction from Hamiltonian cycle to TSP instead of from let's say instead of from 3-sat to TSP. Okay. All right, so let's do a reduction from Hamiltonian cycle to TSP. So if you have a instance of Hamiltonian cycle, okay, then what we're going to do is, so Hamiltonian cycle has an edge set, E, right? And this is not all pairs of edges, as we said, okay, because you don't have a complete graph usually for Hamiltonian cycle. Okay. So now we're going to use this edge set for Hamiltonian cycle to create these distance values in TSP. So what you're going to do is, if two nodes are connected in the Hamiltonian cycle instance, okay, so here you have this graph G, okay, so if these two nodes are connected in G, then you're going to produce another graph, let's call it G prime, okay, so this is also going to have the same set of vertices, okay, but the edge set is going to be sort of all edges, okay, but it's also going to have a distance function on this edge set. And what we're defining over here is this, the distances between pairs of nodes. So if two nodes are connected in the original G, then in G prime, their distance is going to be 1. Okay? And if the two nodes are not connected in G, then their distance in G prime is going to be 2. Okay? All right, so now the claim is that this TSP instance has a tour of length less than n, okay, where n here is the number of nodes. Okay? There's a tour of length at most n if and only if the graph is Hamiltonian. Okay, and the reason is that if the graph is Hamiltonian, okay, then this would imply that this tour, let's call it t, okay, is less than n. Okay, so let's do this direction first, and this is because if you have a Hamiltonian path, right, so let's say you have a graph like this, right, so then we can go through all of these nodes, once. Right, and the edges that we use, okay, in the TSP instance, okay, in the G prime, okay, all of these edges are the edges that come. All of these are edges that are part of G, okay, that are part of this E node, right? So, all right, let me do it again. So we have this is going to be our G, let's say, okay, and we're going to transform this to a G prime, where here these edges are all going to have distances 1, right? And this is going to be 1, and this is going to be 2 over here. Okay, this is going to be the G prime. Okay, and now because let's switch to blue over here. Okay, and because this thing has a Hamiltonian cycle, right? Then we can just take the exact same Hamiltonian cycle in G prime. Okay, and this is only going to use edges which are part of G. And those edges all have weight 1. And so because the cycle has n edges in it, right, then the total length of the cycle is going to be just n. Okay, so when there is a Hamiltonian path, then there is a way to go through all of these nodes with distance at most n. Okay, and then for the other direction, right, so if there's a way to go through all the nodes with distance at most n, right, then it must be that you can never use any of these cos2 edges, right? Because since you're going through all the nodes, you have n edges, and if you ever use a cos2 edge, then your cost is going to be larger than n. Okay, so because your total cost is less than n, you can never use any of these cos2 edges, so you must be only using these cost1 edges, right? And these cost1 edges are all edges in the original graph G. So that means that if you can have a TSP of length less than n, in this G prime, then you have a Hamiltonian cycle in G. Okay, so therefore we've proven this statement, and we've shown that Hamiltonian cycle reduces to TSP. Okay, so yeah, so any questions about anything? All right, so so that's the end of the lecture, and on Thursday we're not going to have a midterm exam. We're going to have another lecture. Okay. All right, so then I'll see you guys, or yeah, I'll see you guys online on Thursday.